Good day. In our last class, when discussing limit at infinity, we observed that limit at infinity is of two types. That is, finding the limit of a function when x tends to positive infinity. Okay, we say that if this is L, okay, we say this L is the limit of that function. Also, we have equally said that when finding the limit of a function as x tends to negative infinity, okay, that is when s is decreasing, okay, to large negative number without bound, okay, we have also said that it's possible for us to have a limit for that function, okay. This is illustrated with a given example: f of x equal to x squared minus 1 all over x squared plus 1. So here we have seen that when s becomes positive without bound, or when x become positive, when x become negative without bound, okay, the solution of this function is 1. Okay, so this little illustration has a specific meaning in mathematics. Okay, this is known as, if this happen, if this limit when x tends to positive infinity happens, or this this is what we refer to as a horizontal asymptote. Let us give a formal definition of that. Definition: here we say the line y equal to L, that is where L is a real number, is called a horizontal asymptote of the curve f of x. Okay, that is y equal to f of x. Okay, so if either the limit of f of x is equal L, or the limit of f of x as x tends to negative infinity is equal to L. Okay, so this is what referred to as horizontal asymptotes. So a good example of this, as we have said earlier, is a curve which behave this way. Okay, so we see that as x becomes large from the right, okay, the curve of this function f of x equal to x squared minus 1 divided by x squared plus 1, okay, it tends to 1 from the right. That is when x becomes large from the right. Okay, so also when x is decreasing, okay, to the negative part without bound, okay, so the curve also approaches 1 from here. So this example is a good example of a horizontal asymptote. So another example which has two horizontal asymptotes is a function f of x equal to tan inverse of x. That is, if you are given the limit of tan inverse of x when x is positive infinity. So this is giving us pi over 2 in radian or 90 degree. Okay. So also if s is decreasing to negative infinity, okay, so the value of tan inverse of x is negative pi over 2. Okay, so this is an example of a function which has two horizontal asymptotes. Okay, this is because as x tends to positive infinity, okay, so evaluating this becomes pi over 2, and when s is decreasing to the negative without band, okay, so the tan inverse becomes negative pi over 2. So the graph of this is how the graph of this look like. Okay, so let's say this is positive pi over 2, this is negative pi over 2. Okay, let's have the line of this. Let's have the line of this. So what this is saying is this. Okay, so this line passes through this line. Okay, when it's become positive, okay, the line approaches the line of pi over 2 as it's become positive, and then when s is decreasing, okay, this curve is also approaching negative pi over 2. Okay, when it's going to when this curve is going to negative infinity. The next is to see how to find limit at infinite value. Okay, whether it is tending towards positive infinity or negative infinity. So the first example we want to consider here is the limit of a function 3 minus 1 over x squared as x tends to negative infinity. Okay, so in evaluating this function, okay, we see that this is a constant, and then this is a function over x. Okay, so when applying the properties under one of the one we discussed under the finite value, okay, we can apply the property 1, which is when we have addition and subtraction form of a function. Okay, so this limit can act on each of the function. Okay, so this will be the limit as x tends to negative infinity, okay, minus the limit as s tends to negative infinity. This. Okay, so we have earlier discussed that the limit of a constant is a constant. So here, the limit of 3 irrespective of what is here is 3. Okay, again, the limit under the limit property 12. Okay, so this is the case when r is 2. Okay, so when we find the limit of this according to the limit property 12, this is 0. Okay, so accordingly 3 minus 0 is 3. Another example is this, where we have the limit of 2x squared minus 5x plus 9 all over 4x squared plus 7x plus 1. Okay, so when we apply this limit to all the functions here, okay, we'll see that applying the limit law, okay, when this affects this becomes large, this also becomes large plus 9. Okay, so a very large number plus 9 will give us a very large number. Okay, so the same thing applicable to the denominator. Okay, so in our earlier video we have said that this case is not a number and hence it is inconclusive. Okay, so what we now do is to redefine this function in such a way that we can be able to evaluate it with the limit. So in order to do this, we look for the highest value of x in this function, and then factor it out from the numerator. Also, we'll do the same to the denominator. So this will be equal to the limit as x tends to infinity. Okay, so when we factor x squared out from the numerator, this will be, okay, so factoring x squared out here, so the remaining term here will be, so this will be 2. Okay, since when we factor x squared out here, okay, so this becomes 2. Okay, and this becomes 5 over x, and this becomes 9 over x squared. So similarly for this becomes 4 or 7 over x, okay, plus 1 over x squared. Okay, so accordingly, x squared will cancel x squared. Okay, and we'll be able to apply this limit to each term in this function. Okay, so going by the properties of limit, okay, this becomes a limit of a constant, okay, which will be a constant. Okay, the limit when applied to 2, it becomes 2. When this limit applied to this, okay, according to property 11, okay, this is 0. Okay, so again, when this limit is applied to this function, okay, according to property 12, this becomes 0. Okay, again, when this limit is applied to 4, okay, this is a constant, it will be 4. If this is applied to this, according to property 11, it is 0. Okay, if this limit is also applied to 1 over x squared, according to property 12, it's also 0. So this becomes 2 divided by 4. Okay, and this is 1 over 2 accordingly. Okay, so the limit of this function as x becomes large, okay, is 1 over 2.